Exactly. Thank you. Hi to everybody. It's a great pleasure to be here for me, and at this stage it's pretty obvious. Many thanks to the organizers. You're doing a great job in organizing this nice workshop. And I come from Pavia, the physics department of Pavia. Our group is the Quit group. Somebody yesterday made me notice that it's quite a funny name, like if you are quitting doing research. But we are not actually, we are just a quantum information theory group in Pavia. And so I will present as a brief overview of my results, which basically is, they are an outcome of my PhD research and thesis. I will present, I will try to stay self-consistent because my research have been at the border of quantum field theory, quantum theory as such, and quantum computation. So I will try to stay consistent. Feel free to make comments or questions during the talk, if we have time, of course. So I will start introducing this computational model of quantum cellular automaton with an application to quantum field theories in general, and then moving to the quantum walk model, which is the simplest one in the context of quantum cellular automaton 1. Presenting the physical assumption of the model for this theory, because this is a physical theory in this QCA computational model, and also presenting how the dynamics can be studied in the relevant graphs of this theory, which are called Calligraphs. Then I will present the mathematical methods we developed to study the dynamics on this kind of graphs. Some classification results relevant to the isotropic case of quantum walks on lattices. And then as a final part, I will move to the actual derivation and presentation of the Weil-Dirac quantum walks, giving the Weil-Dirac dynamics in some regime in this kind of context. And then also closing the talk with presenting some problems, and such as the group extension problem related to the geometrical aspects of this theory and of the study of these kind of graphs, and also the emergence of the spin degree of freedom from non-abelianity in the general case of group difference from Z to the D. So I will start with this general discrete computational scenario, which is called quantum cellular automata. Is just like an evolution rule in a discrete arena for quantum system, and we can think as a computation of like n infinite and enumerable set of quantum system, finite dimensional quantum system. We just restricted to this case at an initial time t0. Then we can think about these two relevant features of this model, which are a strict notion of locality, which is connected to the causal cone structure of this computation. So we have a finite set of first neighbors for each node of this computation, so for each quantum system. And we apply this kind of general computation provided the locality of this computation. So we can go, is a discrete time computation, we can go to time t1 and so on and so forth until time tn. With this kind of, the rule is the same at each step of the computation, okay? So it is homogeneous in this kind of sense. The idea is originally from Sir Richard Feynman, actually, and goes back to his mentor, Sir Archibald Wheeler. You know the famous quotation from Sir Archibald Wheeler, "It from qubit," which is this kind of information theoretic paradigm for treating for treating physical theories in general, and in fact this is connected to the well-known Church-Turing-Deutsch thesis in a strong sense, in a strong physical sense. The question here is, can a universal computation simulate every physical process? So this is our main question. Starting from a simple non-interacting scenario, so free particle. We did at this stage of the work everything as a one-particle model, so it's free, it's non-interacting in this sense. And the QCA theory restricts to the linear case, the case of a linear QCA in the non-interacting case, and that's what we call a quantum random walk. This is a good, turns out to be a good simulation tool, starting from the 80s actually, in lattice gauge theories, but in recent times we saw that it can have also fundamental interest in treating this kind of problem. And the core question is this: may a relativistic quantum field theory be encompassed by the processing of elementary quantum system? There is already a great deal of works of publications in this respect. We have some groups in France, Mlodinov, if you know him, in the UK, in the USA, I mean, and also our group, to give a partial response to this question. So, taking a step back, I want to show some simple classical case of random walks, which goes back to Einstein and the problem of Brownian motion. I think you can know about that. In the discrete case, in the discrete classical case, we can see a random walk as a homogeneous Markov chain on graph. So we have this discrete distribution probability with a neighbor scheme, and we have the probability associated to each node to make a transition for the walker from a node to another neighbor site. And okay, my computer today decided not to plug in the outlet of Qturn, so I had a fancy video here. So I ask you to use your imagination. This was like just a movie of the Brownian motion. So in the continuous case, we can just think this microscopic theory of Brownian motion made by Einstein as the resulting outcomes of the kicks made by the microscopic particles to the Brownian walker that undergoes this Brownian motion through the liquid or something, the mean. Okay, and in the continuous case, we have the well-known Fokker-Planck differential equation with the drift coefficient, the velocity of the walker, and the diffusion coefficient. Okay, so what we are describing here is the evolution of the probability distribution in the classical case. When things go quantum, it's actually a little more complicated and also more exciting, more interesting, because we have, okay, in the classical case, we have, this one is called, by the mathematician, the drunken sailor's walk. Okay, so we have stochastic trajectories, but which are stochastic, but without superposition, of course. They are classical trajectory. In the quantum case, when the walker go quantum, we allow, in general, we allow both for superposition in space, in the space degree of freedom, and also, in general, superposition and entanglement with space with respect to the intrinsic degree of freedom, so the spin of the walker, which is that we can think as located in each node of the graph. So the first simple model, the first simple model in this respect was given by Aronov and other in 1993. And we can see in this simple model, which is not the most general one, the chirality of the state and the evolution of a superposition of this spin state in a one-dimensional lattice according to this chirality. Okay, in a superposition we have that both the components evolve in their respective directions. So this is the core idea of a quantum random walk. Mathematically speaking, we start from a general lattice, okay, with for each node a neighboring site scheme, and to each node we assign also, which is finite because we want locality, and we assign to each node a finite dimensional Hilbert space called the coin system because it mimics as an intrinsic degree of freedom a quantum coin toss. Okay. And the total Hilbert space is the direct sum of the total Hilbert space of the walker is the direct sum of the Hilbert space of the single coin systems. And if we impose linearity to this model, so if we have a genuine quantum walk in the non-interacting case, we can translate this model into an evolution operator, which we request to be unitary, with a notion of translation on the graph, and the notion of transition on the coin system. So we have the transition S times S matrices acting on the coin state, and also a translation on the graph, as I shown you before in a heuristical way. So proceeding constructively, we can think of the state of our walker as an SG in general. This SG is different for each node. Okay, so an SG dimensional vector associated to each node, and we can. Okay, we can associate a transition matrix, as I shown you before, to each edge of the graph, and then we can also formally compose the path along the graph as a sequential composition of the edges H1, HM, which are in this set, which I call S, capital S. Okay, and they are in principle different for each node and for each neighbor scheme, okay, but finite. So we can start with the physical assumption very quickly. We want to model physical law in some way with this kind of model. So we want to have some symmetricity requirement, minimal requirement, which are reciprocity. So if a node, as I shown you before, if a node interacts with another node, the second node interacts with the first one. So reciprocity is a symmetricity requirement on the transition matrices. Then we have locality, as I told you before. So the neighbor scheme is finite, of course, for each node. And the number of edges is the same for homogeneity. We want this physical law to be homogeneous, is the same for each node. The space, the Hilbert space of the coin system is the same, and also the transition matrices, so the physical law, the flow of information along the node is the same for each node. And this physical assumption, this very physical assumption of homogeneity implies that the graph of interaction is a Calligraph, and I will explain later what this is. The last physical assumption are isotropy, which is an assumption on the flow of information along the graph. So we want that there is no preferential, as in classical theory and relativity theory. We want that the flow of information doesn't follow a preferential direction. Okay, so we formalize it in terms of automorphism of our space, of our total space, so the graph G. And we want that these, you see, we have I used to have had a transition here. So you see that here we can exchange the edges of this graph remaining in the same graph. So this is an automorphism of the group, and we want that this automorphism of the group, which leaves the graph unchanged, is represented in a faithful way. Okay, this is a technical requirement. Is represented in a unitary and faithful way by an isotropic group which acts by conjugation on the transition matrices. Okay, so the flow of information is equivalent in each direction. And also, of course, we want unitarity. which leads to unitarity constraints for the transition matrices, and is the selective principle of our theory, the selective principle for graphs and dynamics. As I was saying before, our ambient space are calligraphs, which are like the pictorial graphical counterpart of finitely generated groups. So not Lie groups, not continuous groups, but groups which are discrete, possibly infinite. This is the most interesting case for our purposes. So to construct a calligraph of an arbitrary group, we start in a group theoretical way from the free group, in which each path is inequivalent to another one. So it is a tree, for those of you who are accustomed to this kind of theory. And then we make the quotient with the relation, the closed path that we want our group to have. For example, in the abelian case, here this is called the relator of the group, and this is a presentation of the group. So we have to choose some edges as before, and a set of relators which gives you the commuting path in the case of abelian groups, for example. So go up and right is the same to go right and up. But we can have every kind of groups that we can think of, also non-abelian groups. We just encode this information of the equivalent path into these relators, and this gives us a presentation of a group. So the same group can have different presentation. This can be clear, I think. We can choose different edges for different generators for our group, but every calligraph corresponds to just one group. Okay, here we have another example of the dihedral group, the finite dihedral group D3, I think. Yes. Okay. So quantum walks on calligraphs are nicely described as with the right regular representation on the calligraph of the groups. So we have the translation and the transition matrices. The isotropy requirement translate into this covariance under the action of the isotropy group on the physical law, which is W in this free scenario. And unitarity translates into unitarity constraints, which are these quadratic constraints on the transition matrices, which we want to solve to single out specific dynamics for our model. So as we can study, we have this method. I interestingly listened to the previous talk by Pedro. We have another method to study the dynamics on this kind of graphs with a group theoretical manipulation. We define the right regular representation in the case of abelian group, but this is the case that in a silent way people take as take into account without stating it in most cases, and we want to go beyond also. So we can define the one-dimensional irreducible representation in the abelian case, which are labeled by this quasi-momentum, it is called in this context, which will play the role of our momentum in this model. And the eigenvectors will be given by just the plane waves on the graphs, okay, labeled by the quasi-momenta. So we can diagonalize in this basis our updating rule for the walk, our walk rule, and define an effective Hamiltonian. I mean, which is also called the interpolating Hamiltonian. Okay, defining the rule in the momentum space, the update rule in the momentum space. So we can move to study differential equation in the momentum space. This is pretty a standard method in this context. And we can see that what we obtain is in general a Schrödinger-like differential equation, which has the same form in this momentum space when we anti-transform anti-Fourier transform. The same form of the Fokker-Planck equation, which I shown you before. So we have the group velocity with this parameter omega, parameter function, sorry, omega, which is the dispersion relation of our system, and also the diffusion coefficient. So the dispersion relation is given by the eigenvalues of the evolution operator. And they play the role of velocity when differentiated one time, and the diffusion coefficient in general. Okay, so I can move to present the first idea that we had to study this kind of dynamics, which is also inspired by group and by finitely generated group. The first thing that we can do is to partition our group, is to study a target subgroup of our total group. So to consider a partition into right or left equivalently coset of a subgroup H into G, and consider the unitary equivalence made by splitting the total space into a part moving, a walker moving in H, into H, and an enlarged coin system. So this is what we call a coarse graining of a quantum walk. So we can enlarge the coin system and study the dynamics. For example, this turn out to be useful when we don't have an abelian group. This is a not abelian group with cycles of order 4 in it, and this is interesting because this contains a finite index abelian subgroup, which means that it contains finitely many copies of z to the 2, to the power of 2. So we can study a walk with an enlarged coin system tessellating the graph. We can study a walk on z to the 2 with a different, with our new set of generator on this group. And this allows to study the dynamics in the momentum space, also in the non-abelian case. So we managed to prove this first result that states that if we have if we have scalar quantum walk, so algorithmically the simplest case, the dimension of the coin system is 1 for a scalar walk, and a regular lattice, the dynamics is trivial. So what we did as a first explorative step is to define the first scalar quantum walk on a non-abelian group, which is the infinite dihedral group. And so this is scalar in the sense that each of these element matrix element is the scalar transition for the scalar quantum walk on the dihedral group, on the infinite dihedral group. And we connect this one to a walk, as you can see, in one dimension, but which is a walk with a spinorial degree of freedom, so a coin system of dimension 2. This theorem and this result generalize this classic work by Meyer. Okay, going quickly, so we studied the dispersion relation of this simple work, but I will skip this one because we generalized this result. In the context, as a first step of isotropic quantum walks, so we managed to classify the isotropic groups in the abelian case, in the case of lattices, studying the isotropic group, proving that the isotropic group is always finite. And we classified out of an infinite family of possible graphs. We singled out the unique graphs in each dimension 1, 2, and 3, classifying also the walk on these graphs. So in dimension 3, I make you notice that we don't have a cubic, we cannot implement these walks into cubic lattice, but we have a BCC lattice. So we derived the so-called 3D Weil quantum walk which gives the Weyl equation for small momenta, so in the relativistic limit in this microscopic context, and for no-Robin state on the BCC. And this end up with a full derivation from informational principle of the Weyl equation. The Dirac quantum walk was derived as a coupling, as a minimum coupling of two Weyl walks, and this gives the Dirac equation in the limit and the Dirac dispersion relation. If you are interested in the literature, and in our group we also derived the Maxwell quantum walks, so free QED. And also there was the study of the symmetry group of these walks, which is a nonlinear representation, interestingly, of the Lorentz group. So it is there are some interesting problems related to the geometric interpretation of this model. I do not have time, unfortunately, right now to go in deeper into these problems. But we know that we can connect in this nice mathematical discipline, which is called the geometric group representation. We can connect graph matrix, counting matrix, or Manhattan matrix, as it's called, to a continuous matrix. So also in the non-zero curvature case, so the Poincaré disk or whatever. This notion leads to the construction of groups and the classification of groups on the basis of the emergent geometry for our model. So in the abelian case, we have the groups which are called virtual abelian groups. We managed to classify them and to study them via this coarse graining procedure, which I showed you before. I will keep the group extension problems, and I just so I can just focus on this one. Exactly, last slide. So we have we can let the spin degree of freedom emerge from this construction, just imposing the emerging geometry, for example, Euclidean one, and we can start from a scalar quantum walk and just let the spin degree of freedom emerge emerge as an intertwining between the two isomorphic copies of Z to the 2 or to the 3. So, as I was mentioning before, I would like to talk with, I don't know, Burak or some of you who are interested, also Pedro, about these open problems, because it would be interesting actually to solve this kind of dynamics also in the non-zero curvature sector of this theory. And okay, two possible future direction, but the curved one and also the full nonlinear quantum cellular automata one, which can be possibly interconnected at the end. So I will skip the summary. These are the publication of the work I presented. And this is the group, this is the Pavia group. I want to thank you, John Templeton Foundation, for funding us. Now I'm switching to operational probabilistic theories, so new research on the way. And I owe many thanks to my group, which is a wonderful group to grow as a scientist, I must say. So thank you for the attention. And sorry for being late.
No, it's perfectly fine. So thank you for the very nice talk. We have time for 2-3 short questions, maybe.
Thanks. So, in general, when you take the continuum limit of these models, you get the Dirac equation, right?
Yes.
So, but you show also the Schrödinger equation. So, is there standard techniques to?
Also, sorry.
You show the Schrödinger equation, the continuum limit, right?
Yes, I wrote Schrödinger equation is a Schrödinger-like equation.
Okay. So
Yes, where you have an Hamiltonian, and in fact, Dirac equation and Weyl equation are Schrödinger equation in the sense that they have the same form. Yeah.
Okay.
Yes, exactly.
And also you show I didn't get it well, a three-dimensional case with two walkers, is right?
I cannot use. I think. Okay.
you show a slide in you have a three-dimensional quantum walks
Yes.
with two
Yes, a
walkers. With two
three-dimensional.
walkers or only one?
With two?
Two walkers.
No, with one walker.
One walker.
Yeah, this one, the one on the BCC. Yes, because we have one-dimensional, two-dimensional, and three-dimensional, not on the cubic lattice, which is standard, because this model, yes, when you have a model with more walkers or to non-first neighbor scheme to second, third, you can account for cubic lattice also. But in this model with the original definition of quantum walk, which is the most general, you can just have in 3 dimension, if you want to stay isotropic, of course, you just have the BCC, the bold center cubic. Yes, one walker.
So you also are interested in the curved space, right?
Yeah.
But Pablo Arrighi and Giuseppe Gimofet are working on this type of problem.
Yeah, also Arrighi in France. Yeah, I know, but basically we do not know. Maybe we can also discuss later. But basically we do not know how to link this formalism to the, I don't know, the finite difference formalism and the curvature case. This is the but sure.
Okay, thanks. We have time for last question. Okay, then I just have one naive question. So I didn't get really how non-Euclidean geometry pops out from this construction, from those constructions. So is it because of the group relations that you impose, or?
Yes, exactly. There is this very nice and recent mathematical discipline which is called the geometrical group theory, and it deals with finitely generated infinite groups. And so you can it is very nice because you can connect algebraic properties of groups to geometrical one in a continuous context. So the relators, the set of relators, so the relations, the closed paths, are what gives you, what selects you in this context, the particular continuous geometry. So yes, that is the way.
Thank you. I mean, I would ask more questions, but we are short of
Thank
time.
you. Okay.
Let's thank Marco again.